the last talk has been cancelled, I think we have reached the last talk of this fantastic event. And it is an honor for me to introduce Pavao Mardesic. Pavao is currently undertaking a 6-month visit here in Mexico with the support of the International Research Laboratory in Gasol of CNRS. But this is not the first time we have Pavao here. He has maintained a long-standing collaboration with Mexico, and every day he's becoming more Mexican. He loves spicy food. He knows how to cook with la coche. And recently, he started eating jicama. So I'm very proud of him. But on a serious note, Pavao was my PhD supervisor along with Laura, and I'm very grateful with both of them. They have been of great assistance to me and to many of us. So thank you very much. So with that, the title of Pavao's talk is Infinitesimal and Tangential System Hilbert Problem on Zero Cycles.
Thank you very much, Jesse. So I thank very much Laura for invitation. I'm very happy to be here. It's really kind of, I feel at home here. I have many friends here, and so I must say I love jicama. I love Mexico, but I have to make an effort with jicama. Jicama is kind of my, but I'm trying. Okay, so this is, Jesse told the title, so this is a joint work with José Luis Bravo, who is from Spain, from Badajoz, Dmitry Novikov from Israel, and Jesse and myself. So this is kind of, usually mathematical works are, you have some theorem and you generalize the theorem. And this is absolutely not the situation here. So there are theorems, and in some sense what we do is do a toy example, something which is simpler than what has been classically studied. So I will start with the motivation. So the motivation is something about which Ilyashenko spoke a lot in his conferences. So I'll start motivation. So one cycle so note here it is about 1 cycles, whereas my lecture is about 0 cycles. So of course, a 0 cycle is simpler than 1 cycle. So what is the classical problem? So you take a polynomial f, say from C2 to C. I will think of it rather as being from R2 to R, but it's just for the sake of making the picture. And assume that it has some periodic orbit So the picture, the phase portrait that one has is something like this. So these orbits are gamma of t, which are parameterized by the value of f. So t is the value of f. So one starts with the system df is equal to 0. So I could write the differential equation, which corresponds to this, but let me just write in this form. So df equal to 0, so its solutions are given by the level curves of f, so f equal to constant, and this is what I designed here. And then one takes the deformation. So one takes df plus epsilon eta. So after taking the deformation, so let me look at what happens on a transversal. So one takes a transversal here, and so one starts from some point. And so typically what will happen is that one would start from here, and the orbit is broken. I mean, it can be broken. And this is somehow what one studies. So the difference between the initial point and the final point, which are measured in terms of the value of f, it's what I will call the displacement map, or displacement function. And I will denote it by delta. It's not the same notation which was used by Ilyashenko. Ilyashenko used delta for the Poincaré map, for the first return map. But for me, delta means difference. So it is difference between the Poincaré map and the identity. This is the reason why I denote it by delta. So delta is this displacement map, displacement function. And so how does one study this displacement function? So yes, so this maybe to be to respect my notation later, I will instead of gamma of t, I will put c of t. So c of t is a one cycle. And what we want to study is this displacement function, delta of t. So how is this displacement function obtained? So here, the cycle c of t, there is this perturbed cycle, which I will denote by c epsilon of t, is deformed. And so, how do we calculate this function delta of t? Well, it is very simple, because we measure this distance in terms of the function f. So we have c epsilon of f, and the question is how much do we accumulate the difference of f along this path. So this is simply the integral along c epsilon of t of the function df. I forgot to write here equal to 0. So the displacement function is given by this very simple formula. Note that c epsilon of t is not a cycle. So we start with a cycle. This means a closed orbit, which was the white one, c of t. We make a deformation, we break it, and we have some unclosed orbit, c epsilon of t. So this is the formula. And so this can be recalculated. So using this equation, so df is equal to minus epsilon eta. So I can write this, and so this is equal to minus epsilon integral eta. But so I can, instead of integrating along c epsilon of t, I will integrate here to c along the value. I could write, well, maybe I erase 0. I put epsilon equal to 0. Of course, what I have written for the moment, it is wrong, but the error is small, because the error between, so, okay, there is one epsilon, but there is another epsilon which is hidden in the fact that c epsilon is very close to c. So this is something that is smaller than the order of epsilon. So this is somehow the classical formula which is due to Pontryagin. But I will use somehow as it is often in science, in life, in whatever, a wrong name. So this function, most people, including me, call it Melnikov function. I am aware that it is wrong. It shouldn't be called Melnikov function. Melnikov was later. But somehow everybody calls it Melnikov function, so I will call it Melnikov function, M1, because it's this kind of first Melnikov function. So there are now two questions. So two problems. I will start with the easier problem. Yes, maybe I think I didn't say. So here, eta is a polynomial form. So this function, okay, so maybe I will stress two formulas which I have here. So this is one formula, my function delta, the displacement function, and there is this function which I will write again, m1 of t is equal integral along eta of c of t. So this is Melnikov, so this is displacement. And this is Melnikov. So do you know what type of function is this? How is this called? I think it was, the name was pronounced in Ilyashenko's lectures. So you have an integral of a polynomial form along a curve, which is a solution of a polynomial equation. So such a function is called an abelian integral. This is an abelian integral. So this means integral of a polynomial or rational, it's not very important. It was also in lecture of Musigno, in Di Gessi's lecture, of a polynomial form along solution of polynomial equation. Okay, so two problems. First problem, which I will call tangential. Which is how many zeros of m1 of t. So here I have to be slightly more precise. So the function m1 of t, it is a multi-valued function because somehow, okay, I wrote it for one value of t. If one modifies the value of t, then you can push the cycle to nearby cycles. It depends, one can usually push the cycle. So there are some exceptional values which are essentially the critical values which one has to avoid. And if one goes around the critical values, then one has monodromy. And so this function will be a multi-valued function. But so how many zeros of m1 of t? I would put in parentheses in a simply connected domain. So these functions, we look at these functions as t belonging into some domain. Maybe I write here. T belongs to some domain in the complex C. So this is tangential. I will explain the word tangential in a moment. And the second is infinitesimal. Which is how many zeros of delta. I was not very precise when I wrote delta of t, actually delta is not just a function of t. Of course, it depends also on epsilon. So I should write it delta of t, comma epsilon. So how many zeros delta of t epsilon are born for epsilon close to 0? So why? So first of all, the word infinitesimal. Infinitesimal, this means in a perturbation. You have some situation and you look at a deformation. Tangential, instead of using the word tangential, one could use the word first order, because actually if you look at the equation, I will second blackboard. So we have that delta of t epsilon is epsilon m1 of t plus O of epsilon. This was the formula that we wrote. And so here we are interested in the zeros of this function. And of course, zeros of this function are very much related to zeros of this function. But the two problems are not equivalent. This is only the first order problem. And what is somehow the relationship between the two? It is the implicit function theorem. So the implicit function theorem tells you that if you are at a regular value of t, and where you can apply the implicit function theorem, then each simple zero of m1 of t can be extended to a zero of delta, and then this zero of delta is a zero which is born from m1 of t. Okay. So this is, maybe I should say a few words about what is known. So tangential problem. Okay. In my title, there was 16th Hilbert problem. So 16th Hilbert problem speaks about the number of limit cycles. And so what do these two problems have with the problem of the number of limit cycles? They are kind of closely related. It means that if you have a zero of the function delta, it gives you, if you have an isolated zero of a function delta, this gives you a limit cycle. Because isolated, I mean, what does it mean? Recall, what does it mean delta equal to 0? This means that the displacement is equal to 0. So in my picture, this blue line, it closes. And nearby lines do not close, so it is a limit cycle. What I do not take into account is Ilyashenko's cyclos bandidos. So cyclos bandidos, they can, of course, appear, and they correspond to not fixed point of delta, but periodic point of the Poincaré map. So you take the Poincaré map, and then you go several times around, and then it can close. So of course, a periodic point of delta you cannot see by looking at the function delta. One should be more somehow cautious, but this is not the subject of our study. And by the way, so these cyclos bandidos, they don't exist in the real setting. Because in the real setting, it is just if you have a cycle which almost closes, it would cut itself. It's just a Jordan lemma, which somehow makes it impossible to have these kind of cycles. Okay, so this is the motivation. I think I explained you all the words which appear in my title, except zero cycle. So now the idea is somehow to replace 1 cycles by 0 cycles. So I have to say, what is a 0 cycle? So what is the setting now? So here we looked at this form, df plus epsilon eta is equal to 0. And now we take f, a polynomial in only one variable, g, another polynomial in only one variable. And so we start with the first polynomial. We take f of x is equal to t. So this is a polynomial. I will fix the degree of f equal to m, degree of g equal to n. So yes. Let me suppose that t non-critical. Then we will have m zeros. So we have z 1 of t, z m of t, zeros of f of x, I should put z, f of z minus t equal to 0. Okay, so what is a cycle? So zero cycle. Which I will denote also by C of t. It is a form. It is the intelligent world is a divisor. What is a divisor? This is a formal sum ni zi of t, where ni are integers. Sorry, this is okay. It's like if I have, moreover, the following condition, that the sum of ni is equal to 0. So the sum goes from 1 to m. So this is a zero cycle. And now we want somehow, yes, maybe I give an example which I will use later. If you take just z1 of t or z2 of t minus z1 of t is a divisor, is a cycle. And this type of cycle is called a simple cycle. So the idea is not to perform the difference, to keep it formal, just z2 of t minus z1 of t. Now I want somehow to follow what I have done on this first blackboard. So what have we done here? So here we studied the deformation. We had one form, let's say exact one form, which we deformed. And now we are in dimension, we have a function. We started with f of x is equal to t. And now what do we do? Well, we consider deformation. Which is f of z plus epsilon g of z equal to t, equal to 0, equal to t. Yes. What happens with our cycles zi, with our zeros of f of z minus t. So here I supposed that t is a non-critical value. Non-critical value means that upstairs the derivative is different from 0. So we can apply the implicit function theorem. So I would say t non-critical hence by the implicit function theorem, one can extend the zeros zi of t, and so these extended zeros, we call them zi of t epsilon. So what does it mean? So we have that zi, so we have that f plus epsilon g applied to zi of t epsilon is equal to t. What I have to note is that these functions are hence defined locally, but they will be multivalued functions of t. I will make a picture. So here, downstairs we have a C. In this C we have, I depict some critical values. And now I take a t, which is not a critical value. T, non-critical. And so here upstairs I have C2. So what do I have above this point? I could have done the picture already for the case without the epsilon. Okay, let me do it first for f of zi of t equal to t. So here are the points z1, z2, etc. until Zm. So of course there is no ordering in the complex plane, so it's I put the indices in an arbitrary fashion. And so what happens is, if you go around these critical values, what can happen? So at these critical values, if you come just at these critical values, so there are some of these points which come together. You can think that, for instance, Z1 and Z2 come together. And if you go around, then these 2 points, they will be swapped. They will be exchanged. They will be permuted. So, and if they are permuted, so, I mean, you have what was before called Z1 is now called Z2. What was called Z2 will be called Z1. So it is a multivalued function. The same thing happens when you add the parameter epsilon. Now, okay, so I defined it, the zero cycle C of t. What is C epsilon of t? So it is the cycle I goes from 1 to m. Maybe I will, okay. Ni zi of t comma epsilon. Here I'm cheating a little bit because it depends on the degree of the deformation. So this is like this if n is smaller than m, because then f plus epsilon g will be of degree m also. If I deform by a function which is of bigger degree than m, then my sum here will go not up to m, but up to n. So these are somehow these are zero cycles. So now I kind of defined the objects that we study, the main objects, but there are 2 more objects that I have to define. So now I have to define what is the displacement function or maybe before, what are abelian integrals on 0 cycles? So formally, you have an integral along c of t. So this is notation. Integral along c of t of a function g. So what do you think, what is the definition? So what do we have? C of t is this. And you have at your disposal a function g. So how do you define such an integral? It's kind of an integration, but I mean, one shouldn't be perturbed by the sign of integral because it's not true integration. You are on 0 cycles, you have points. So what can you do with points? You have a function at your disposal. This is the function g. You can calculate the value of g at these points. So this is by definition. So here you have the sum. I goes from 1 to m. And I, g of zi of t. So this is kind of, it is simpler than the case of integration on 1 cycles, and this is what makes it kind of more difficult, because you are not accustomed to this situation. You have a function which is a 0 form. How do you integrate a 0 form? You evaluate the function at the points that you have at your disposal. So this is the definition. And now we can, so this is well defined for t belonging to C minus, I will denote it by sigma. This is a set of critical values. Okay, if you have a CR of t of G, so then it is sum I goes from 1 to m, and I G of Zi of t, comma epsilon. And now finally, we come to the main player in the story, which is the displacement function. On 0 cycles. So what is the displacement function? Look, the idea is to do the same thing as what I did before. So on 1 cycles, what was the definition, or not definition, but how does one calculate the displacement function? One integrates along the deformed cycle the form df. So here I do the same thing. So this is, so delta of t epsilon is the integral along c epsilon of t. So yes. So what is somehow the equivalent of this relation? It was this expression. So somehow what plays the role of df, it is simply f. So we have integral along this of f. What does this mean? Well, here I gave the definition. What one gets if one integrates any function g along some cycle. So this is the sum. I goes from 1 to m, and I f of zi of t epsilon. maybe it's a moment to make a stop, so if you have some questions. Maybe I recall briefly the situation. So I think this is a situation which you are kind of familiar with and which you know. And somehow the idea is to do a situation which is a study which is simpler. But it's not simpler but less familiar. So one takes 0 cycles. So instead of looking at this deformation, one looks at the deformation of just one function of one variable. This was this deformation. So this is polynomial, this is polynomial. And now somehow here the main actor were cycles, which corresponds to level curves of f. These were level curves of f. And here also, in some sense, you take level curves of f, I mean level set of f, but level set of f, if f is just a polynomial, is just points. So you just take points. These are my points zi. And then, with these points, I make a cycle. A cycle, so it's homology. You must have, it's zero homology. Zero homology, it's a formal sum of some points with some coefficients where the sum of the coefficients is equal to 0. You have that this is equal to 0. And as I recall, this is the simplest case is a simple cycle. And when you add, so this epsilon g, it deforms these roots. Instead of looking at the equation f of z equal to c to t, you look at f of z plus epsilon g of z equal to t. And now the displacement function, so this is our definition. It didn't appear before, but it is exactly the exact analog of the definition in the one cycle case, that you integrate along this deformed cycle the function f. So you obtain this. Okay, now how can this be calculated? So recall that we have this relation that f of z plus epsilon g of z is equal to t. So this is sum, I go from 1 to m n I. So instead of f, I will write t minus epsilon g of z. So I take t minus epsilon g of zi of t epsilon. So this we can write as two sums. The first sum is t times the sum I goes from 1 to m n I. But this sum is equal to 0 because this was the assumption on a cycle. We have that this is equal to 0. So this, maybe I will write it. This is t times sum I goes from 1 to m n I minus epsilon sum I goes from 1 to m g of zi of t epsilon. So this term is equal to 0. And what is this term? So this is minus epsilon times this guy. And who is this guy? This is the integral, exactly, this is the integral of g along the cycle c epsilon of t. So this is the exact formula. This is exactly the same thing as what we had here. And now we do the same thing as one does here. So one recalls, okay, what did we do here? We say, okay, epsilon we take outside, and c epsilon, this we replace by c plus a small term. So this is, maybe I'll write it here. This is, so minus epsilon, integral along c of t of g, so I put here epsilon everywhere equal to 0, plus small o of epsilon. So this is exactly the same structure as what we had before in the case of 1 cycles. So this function we will call the first Melnikov function. Yes, I didn't write, sorry. No, this is right. Yes, I wrote it there. And so this function, which appears here, we'll call it m1 of t. So it makes minus epsilon m1 of t plus O of epsilon, which we call this. So first is because it is the first which can appear. But here we work only with this one, so I will just write it Melnikov function. And so now I am ready to somehow explain finally what is infinitesimal and tangential problem, 16th Hilbert problem on 0 cycle. So I will start with tangential, which is easier. On 0 cycles. So it is so we consider the equation m1 of t equal to 0, and the question is how many zeros does this equation have? So it is always on 0 cycles here. Infinitesimal it is how many zeros of delta of t epsilon equal to 0 are born from epsilon equal to 0. Now, the advantage of looking at this simpler problem is that we can solve it. Did you understand the questions? So maybe I will, so this number, we call this number, so we call it, Z1 of f gc. 1 is for first Melnikov function, somehow first order term. No, so this I should write in tangential, so here it is delta. And here, this number we call Z1 of f g and c. And as you know, in 16th Hilbert problem, what one wants to do, what one would like to do, is to have a bound which is dependent only on the degree, not on the system itself, but on the degree. And so how is here the bound? So here the corresponding problem is, so if here we have Z1 of Mn, so this is the maximum of degree of f if it is at most m, degree of j at most n, and for any cycle of these numbers which I wrote here, z of f gc, and similarly z delta of mn is the maximum of these numbers z delta. So here I should put 1.
And what is C?
C is the cycle, any cycle.
So F fixed, G fixed, and C arbitrary.
So here is for F fixed, G fixed, and C fixed. And here I vary all F, I vary all G, and I vary all C. So it is the same, so degree of F less than or equal to M, degree of G less than or equal to N, and C any. Any cycle. So let me say the main results. So theorem A. So we have F, degree of F is equal to M, degree of G is equal to N. So first, if M is bigger than 2, and M does not divide N, then Z1 of Mn is equal to N times M minus 1 factorial. 2 is if M is bigger than 2, M divides N, then Z1 of Mn is equal to N minus 1 times M minus 1 factorial. Third case, if M is equal to 2, then Z1 of Mn is the integer part of N minus 1 divided by 2. Está abajo, ok, gracias. And theorem B. So this was, so the first theorem that I wrote, this concerned the tangential problem. So the problem of the zeros of abelian integrals. And the second one, it is for the infinitesimal problem. ¿Me das 3 minutos? 5. Okay, so we always have the degrees are the same. And so the first case is if n is smaller than m, then z delta of mn is n times m minus 1 factorial. If n is bigger than or equal to m, then, so there are two cases, if m does not divide n, then z delta of mn is equal to m times n minus 1 factorial divided by n minus m factorial. B is if m divides n, then z delta of mn is m times n minus 1 factorial divided by n minus m factorial minus m minus 1 factorial. And if m is equal to 2, then z delta of mn is equal to n minus 1, the integer part of n minus 1 divided by n minus 2. So what I insist here is that the bounds that we give are optimal. So this is not just a bound, but the bound is attained. So this is kind of, I would say, a dream of what one would like to have as a result in the 16th Hilbert problem, somehow get an explicit bound, how much cycles one has. And of course, despite the work of many people like Ilyashenko, we are very, very far from attaining such a goal. The other thing I wanted to say is if you compare the two theorems, maybe I will put it down here. So the first case, in this first case, you have this bound. This is the number of zeros of abelian integrals. And this is the number of zeros of the displacement function. And the two coincide. So this is somehow also something that many people think that it is always true, but it is not. It is true if one can apply the implicit function theorem. But if you look at different cases, one sees that it is not the same. So the number of zeros of the displacement function can be bigger than the number of zeros of the Melnikov functions. Such zeros of the displacement functions which do not correspond to zeros of Melnikov functions are called, the terminology was introduced by Roussary, alien cycles. The reason is that one cannot apply this implicit function theorem. So you have, for instance, if you are in the classical situation, if you are in a polycycle, you have, say, a system like this, and then all zeros here correspond to zeros of the Melnikov function, but here the first return map, the displacement function is not differentiable, and so you cannot apply the implicit function theorem. So you can have zeros which do not come from zeros of the abelian integrals. The same thing happens in this case. There are also some phenomena which I don't have time to speak about, like Chebyshev property. And so somehow the idea is that even though this situation is much simpler than the classical situation on one cycle, it is sufficiently rich, and all somehow famous phenomena that have been intensively studied for one cycles are present here. And so I didn't have time to say a few words about the proof, but somehow the idea is that some techniques can maybe be transported to study the classical problem. I will stop here.
Is there any questions for Pavao?
The expected or guess or result for the actual problem are of that kind? Those big numbers?
I think it's not very, it's really very hazardous to say what is expected, because we are really very, very hard. So what exists now is best. So for the infinitesimal problem, I would say that there is no result which exists. For the tangential problem, there is the result of Khovansky and Dvarchenko who prove finiteness. So there is finiteness, so it's the existence of this number, and there is the result of Beniamini, Novikov, and Yakovenko, who give a bound, but which is horrible. It is a double exponential bound. So it has nothing to do with something like this. Of course, here, I didn't have time to say it, but actually, all we do is algebraic. We don't exit the algebraic world. We are not in the transcendental world. So I think that the bound is not much worse than this, but I mean, certainly new techniques are necessary to prove it. And so it is, I mean, if one has a double, so the proof, the result of Beniamini, Novikov, and Yakovenko, it's, I think, a double exponential of a polynomial of degree 62 or something like this, in function of n. So he takes, say, they take m and n to simplify the same. Then you have just one parameter n, and it is exponential of a polynomial whose coefficients are not determined, which is of degree 65, and somehow, so it's, I mean, it's horrible. It has nothing to do with this, but this is somehow due to the way how the proof is done.
Or examples of systems like this with many.
So I think that the best example that exists is obtained by Colin Christopher, and if I recall well, I think it is n squared logarithm of n. The asymptotic is n squared logarithm of n. So it is somehow, if you take n and m the same, it's not somehow too far from this kind of so this is somehow the lower bound. And on the other hand, there are, I didn't have time to speak it, there is a Chebyshev property. This is a property which is, if you have a system of functions, they satisfy the Chebyshev property if the number of zeros of linear combinations of the functions is less than the dimension of the space. So the main examples are polynomials. You take a polynomial of degree n, it is, as a vector space, it is of dimension n plus 1, but of course a polynomial of degree n can have at most n zeros. And it has been a conjecture by Arnold, not for the infinitesimal, but for the, say, tangential problem for abelian integrals, that, there is this big book of Arnold's problem, and it appears many times in different forms in his book. But essentially, somehow the formulation is that in natural problems, abelian integrals form a Chebyshev system. So that means, I mean, the dimension of the space is easy to calculate. So it is known, there are known examples where it is not the case. There is an example by Jolondek and Christian Rousseau, where you have abelian integrals which do not form a Chebyshev system, but somehow this difference between the two is not very big, between the dimension and the number of zeros. And in this zero-dimensional case, we compare the two, and we show actually that the quotient goes to infinity. There are much more zeros than, asymptotically, there are much more zeros than the dimension of the space of abelian integrals. So I think this is also something that is kind of interesting. So I think that it gives some ideas about how things hopefully could behave, but it is very, very far from even from a strategy for attacking the general problem. One case which we did look at is if you take a hyperelliptic abelian integral, so you have y squared plus p of x, then it is easy to get something which looks very much like a zero-dimensional abelian integral, but there is a parameter t which somehow disturbs the argument, and so it doesn't work. But I mean, we are working on a continuation.
Thank you.
Any other question?
I see your yellow square. No?
Mm-hmm.
This is a family of polynomials.
Yes.
And a family of Riemann surface of the corresponding polynomials.
Mm-hmm.
I see two very qualitative different cases, which n is less or equal than n.
You mean between this and this?
N is greater than n. No? Because when n is greater than n, then the change is instantaneous.
You
What is the meaning of this in your
you are right. I didn't have time to speak about it. So this is if you have n bigger than m, then you at infinity, so this is singular perturbations that you have. This corresponds to, this is exactly a singular perturbation. What is a singular perturbation? Is somehow a regular perturbation. You have some system and you perturb, you put plus epsilon something small. But if you have some system plus epsilon something big, this is a singular perturbation. And at infinity, this is what happens in this case. And so you have, this is the case where you have a big difference between the infinitesimal problem and the tangential problem. And this is precisely that you have the appearance of alien limit cycles from infinity. So you have cycles which come from infinity, which are you have solutions which are solutions of the infinitesimal problem, which do not correspond to any solution of the tangential problem.
More questions?
Is there a combinatorial reason why you get like a factorial on results?
Yes. So I didn't ask you to ask the question, but thank you for asking the question. So the general idea, maybe I explain it here. So how do we calculate? So in the simplest case, how do we calculate this number? We take intersection between a curve and a surface. So what is the curve? The curve is given. I will cheat a little bit. So we have a curve which depends on on f, which is essentially the number of z1. So you look at z1 to zm such that f of z1 is equal to f of zm, which is, by the way, is equal to the t. So you have this curve, and on the other hand, you have a surface S gamma, Sg, which is given by, where is it? I must have written it. Abajo. So it's given somehow by this G. And this factorial m, it comes from this equation. So this is a curve, and you look at the degree of this curve. In order to see the degree of this curve, you look at the intersection of the curve at infinity. And as you have a polynomial of degree m, then how many points does it have at infinity? Well, it has m points, but then as you want to have a point at infinity, so in projective coordinates, you put the last coordinate equal to 0, and the one before, you can homogenize and put it equal to 1. And then you have m minus 1 coordinates in this story. And as we are not interested in the points zi, but in the corresponding value of t, one has to take into account all the permutations. And so these are the m minus 1 permutations that there are. And so it is the key of everything is the Bézout theorem. So it's just the Bézout theorem. So this gives you degree m minus 1 factorial, and the surface, there is a surface which corresponds to G, which is of order n, and the intersection of 2, it's just the multiple of the 2. This is in the good case. And in the bad case, like what Musigno asked, then you must take into account the points which come from infinity. You must take into account symmetry, which, for instance, happens in the case m equal to 2, because if you permute z1 and z2, these correspond to the same value of t, and so on.
More questions? Then extend the speaker again.
So as this is the last lecture, I think, I'm sure I will be very happy that all of us thank Laura.